Hi everyone, it's Mrs. Bustamante, and today we're going to talk about quantum numbers. So we're going to identify what the four quantum numbers are by their name and their symbol. We're going to write quantum numbers in order to describe an element's electron's position in an atom, basically tell us exactly where an electron might be, and then determine which electron is being identified by a set of quantum numbers. So before we do all that, I just want to take us back. What have we been talking about? What are some things we need to know? And you would just kind of add notes here as you need. So remember, we've been dealing with Bohr diagrams a lot, and he took the idea that these electrons are in energy levels. He actually says that these energy levels are orbitals, right? Electrons orbit around the nucleus like the planets around the sun. And when he does this, he gives each of them a quantum number, and we've still kind of been using this idea. And a quantum number is just a way to identify it. Really, what we've been calling our quantum number, so to speak, is our principal energy level. So as he's talking about where these electrons are and where they are in the electron cloud, he says the ones that are closest to the nucleus have an n equals 1, right? A principal energy level of n equals 1. And he calculates the distance from the nucleus using this idea. He says the quantum number will increase the further away from the nucleus you get. This is actually not really entirely correct, right? As we know now, we've been using the cloud model, and we still kind of use this idea of orbitals, and that's where an electron will be. But really, two people kind of come up with this model that we use now, and we combine them to say here now we use what was called the quantum mechanical model to describe an atom. So we put together the Heisenberg uncertainty principle and the Schrodinger wave equation, and we call them now our quantum mechanical model, which is how we describe the real model of an atom now. With like Bohr, they say that there are energy levels, but they say that in doing this, we can't know the exact location of where an electron is. We can only kind of make a prediction about it. It's not perfect orbits, but it is generally an area that there can be located an electron in a certain spot. And this is sort of what we've been doing this whole time, but we've been identifying them, right? We've talked about principal energy levels, and we've talked about sublevels in there, and then we've talked about how many orbitals are in that sublevel, right? Because S sublevels can hold 2 electrons, but we see that P sublevels can hold 6. So they have to have 2 suborbitals of the suborbital, if you will, of the P orbital to get to 6. And we've gone through and we've labeled how many electrons you can have in each particular principal energy level and each sublevel, like our SPD and F sublevels, and then how many we can combine together to get our total electrons. And we've talked about when we first started this, how this relates to the periodic table. So as you've been doing your electron configurations, as your teacher made you do what felt like the same thing over and over and over again, the hope was that you were starting to see a pattern. The hope was that you were starting to see what we'll know as group 1 and group 2 are what we call the S block. When you look at their electron configuration, they always end in S. It might be S1 or S2, but these first two groups always end in S. Plus, of course, helium over here, which we put in group 8, because we're going to see that it actually has a full valence shell of electrons, so it behaves like a noble gas. And then when you did all of these elements over here, hopefully you noticed that they all end in P. Okay, so when you're looking at them, when you write their electron configuration, they might end in P1, P2, P3, P4, P5, or P6, but they all end in P. So we call this block of the periodic table the P block. These elements in the middle we call the D block, because when you write their electron configuration, they all end in D. And then these ones at the bottom, these are going to be later, you're going to know they're called the lanthanides and the actinides. And they're going to be your F block. So when you write your electron configuration for them, you'll see it ends in the F block. So what we've been seeing is as we fill electrons into specific orbitals and to specific places, we see a pattern on the periodic table. We see our S block for our first two groups. Our P groups are over here in our nonmetals and some of our metalloids. In our D block, we see transition metals, and then our F block down here are our lanthanides and our actinides. And remember, group 8 over here is special because 8 is great and it has a full valence electron. So remember, it's going to be the group that's really unreactive, and all the other elements are going to want to be like. And we've gone over, hey, what are the shapes of these orbitals? We know they're not perfect circles, but what are they? We know s orbitals are spherical. We know p orbitals are dumbbell shaped, which sometimes your teacher calls peanut shaped just because it looks sort of like a peanut to help you remember. And there's 1, 2, 3 of them that make up your p orbitals, and so they go on that x, y, and z axis. And then we talked about d orbitals and f orbitals. And when we draw them, they just start to look crazy and they go overlapping and they take up the same space. And so that's kind of how we have combined, right, this idea that there are electron orbitals and electrons are probably going to be in that space, but that space is actually three-dimensional and that space overlaps. So even though that might be where an electron is, that's why we see this idea of an electron cloud in a specific place, because they overlap and you find those electrons in different places. And when we've done this over and over again, we've used this nice little diagram to help us know what order to fill those electrons in. And remember, you get this on the test to help you. So you don't have to memorize it, but you do have to memorize that s orbitals hold 2 electrons, p orbitals hold 6 electrons, d 10, and f 14. And this is again what we use to fill our orbitals with electrons.